The night sky hides structures of almost unimaginable scale. We are about to explore 20 colossal cosmic formations that are actively redefining our view of the universe. You will gain a new understanding of the universe's grand architecture, from immense galaxy walls to perplexing empty voids. How did a structure so large it challenges the core principles of cosmology come to exist? What mysterious force is pulling thousands of galaxies toward an unseen horizon? By the end of this journey, your perspective on the cosmos will be fundamentally transformed. How does it change your sense of place to know we live in a vast cosmic web? Spanning 10 billion light-years, the Hercules-Corona Borealis Great Wall is a filament of galaxies so vast it defies easy comprehension. This structure was not found by pointing a telescope at a single point of light. Instead, astronomers pieced together its staggering outline by mapping the locations of distant gamma-ray bursts. These brilliant flashes act like cosmic lighthouses, revealing the hidden backbone of the universe. When the map was complete in 2013, it revealed a formation of thousands of galaxies, a great wall on a scale that many thought was impossible. The very existence of such a colossal structure directly challenges a foundational idea in cosmology: the principle that the universe should look roughly the same in every direction when viewed on a sufficiently large scale. Finding something this immense forces a profound question. Are we seeing a statistical fluke, a rare clustering in our cosmic neighborhood, or is our understanding of the universe's fundamental uniformity incomplete? This discovery does more than just break a size record. It pressures our models of the early universe, suggesting that matter may have clumped together in ways we are only beginning to fathom. The Hercules-Corona Borealis Great Wall is not merely an object. It is a challenge, written across the sky in galaxies and gamma rays, demanding we rethink the rules. That challenge to cosmic uniformity was not an isolated event. Another discovery, the Sloan Great Wall, paints an even clearer picture of this grand architecture. Picture a river of galaxies so immense it would take light 1.37 billion years to travel from one end to the other. This is not a solid barrier but a vast, interconnected highway of galaxy clusters and superclusters. A complex web of cosmic structure revealed by the Sloan Digital Sky Survey in 2003. Its sheer scale is difficult to grasp, a filament of matter that immediately raised the same profound questions as its larger cousin. Does a structure of this magnitude violate the long-held belief that the universe is essentially smooth and uniform at the largest scales? The Sloan Great Wall suggests our cosmos might be far more textured and heterogeneous than our simplest models predicted. More than just a challenge, however, it is a magnificent demonstration. It shows us the universe is not a random scattering of isolated islands, but a carefully woven tapestry. This is the cosmic web in action, a direct result of gravity's relentless pull over billions of years, guided by the unseen hand of dark matter. Every galaxy in that vast river is a testament to the forces that sculpt empty space into a network of breathtaking complexity, forever changing our view from a universe of points to a universe of connections. But the cosmic web is not built from galaxies alone. Sometimes its largest structures are traced not by the steady light of stars, but by the most violent and brilliant beacons in creation. In 2012, astronomers identified a group of 73 quasars so vast it was named the Huge Large Quasar Group, a cluster stretching an almost unbelievable 4 billion light-years across. This is not a simple gathering of objects. It is a continent of cosmic energy, a single structure that, by its very existence, seems to defy the established rules of the universe. Quasars themselves are the key to understanding the baffling nature of this discovery. Each one is the intensely luminous core of a distant galaxy, powered by a supermassive black hole actively feeding on surrounding matter. They are like lighthouses shining across the deepest voids. To find 73 of these brilliant beacons arranged together in a single, coherent group is not just unusual. It is a direct challenge to a core tenet of modern cosmology, the cosmological principle, which suggests matter should be distributed evenly at the largest scales. The Standard Model predicts a theoretical maximum size for such structures, and the huge LQG appears to be far larger than that limit allows. Its discovery forces a difficult question. Are we witnessing a statistical anomaly so rare it tricks us into seeing a pattern? Or is this colossal grouping a signpost, pointing to a deeper truth about the universe's infancy? The immense scale of this quasar group suggests that the seeds for such giant structures were planted in the very first moments after the Big Bang, imprinted onto the fabric of spacetime before the first stars ever shone. It invites us to look closer at these energetic phenomena, not just as brilliant points of light, but as markers revealing the underlying architecture of everything. While the cosmic web weaves a tapestry of brilliant clusters and filaments, it also contains profound emptiness. The Boots Void is a staggering example, a cosmic desert so vast and so barren it defies easy understanding. Discovered in 1981, this region of space spans an almost inconceivable 330 million light-years across. Within this unimaginable volume, astronomers have found only a handful of galaxies, a level of emptiness that stands in stark contrast to the crowded Great Walls we have just explored. The existence of such a void is not the mystery, as empty spaces are a natural part of the universe's structure. The true puzzle is its scale. Why is there a region of nothingness this colossal? Its exceptional size challenges our models of how the cosmos evolved, suggesting that the processes which create these underdense regions might be more powerful, or perhaps more mysterious than we first believed. This void is not a static hole. Its immense emptiness exerts a gravitational influence on the cosmic web around it, subtly shaping the flow of galaxies and the growth of neighboring filaments. The Boots Void teaches a powerful cosmological lesson. In the study of the universe, absence can be as informative as presence. By understanding why such a vast nothing exists, we gain deeper insight into the forces of gravity and dark energy that sculpt the entirety of visible creation. Before the Hercules-Corona Borealis Great Wall or the Sloan Great Wall reshaped our cosmic perspective, there was a foundational discovery that first revealed the universe's true texture. The CF-A2 Great Wall, identified in 1989 by astronomers at the Center for Astrophysics, was a revelation. Stretching over 500 million light-years, this immense filament of galaxies, anchored by the dense Coma and Leo clusters, was one of the first super-large structures ever mapped. Its discovery was a profound departure from the long-held assumption that galaxies were sprinkled more or less evenly throughout the cosmos. Here was undeniable proof that they gathered into vast sheets and immense threads, a cosmic architecture on a scale that was previously unimaginable. This Great Wall did more than just break a size record. It fundamentally changed the course of observational cosmology, forcing scientists to confront a new reality. The universe was not a random, smooth sea of stars. It was a structured, interconnected web. This discovery provided the crucial early evidence for the model we now accept as fact, where the invisible scaffolding of dark matter guides the formation of these colossal filaments, with visible matter like galaxies tracing out its hidden lines. The CF-A2 Great Wall was the milestone that opened our eyes, proving that to understand the cosmos, we had to stop looking at individual points of light and start seeing the grand design connecting them all. Our own cosmic neighborhood holds a grander title than we once knew. We are part of a structure so immense it redefines our galactic address, a supercluster of galaxies named Laniakea, a Hawaiian word meaning immense heaven. This discovery in 2014 did more than just give us a new name. It fundamentally changed our understanding of how galaxies move together on the largest scales. Laniakea spans a staggering 520 million light-years and is home to roughly 100,000 galaxies, including our own Milky Way. But here is the profound shift in perspective. We do not lie at its heart. Our galaxy resides on its remote outskirts, a suburban island in a vast metropolitan web. Scientists mapped Laniakea not by drawing a simple boundary around a group of galaxies, but by tracing the subtle river-like flows of their motion through space. All these galaxies, including our own, are drifting gently on a cosmic current, flowing toward a common and mysterious gravitational center known as the Great Attractor. This reveals that a supercluster is not just a random, static collection. It is a single, coherent structure, a continent of galaxies all moving together under the influence of the same immense gravitational landscape. So what does it mean for our galaxy to be a part of this immense heaven? It means our home is not drifting in isolation. We are caught in a vast, slow-motion river of stars, pulled by forces that operate on a scale almost too large to comprehend. Understanding Laniakea is the first step to understanding the ultimate source of that pull, the hidden heart of our local universe that guides our long-term cosmic destiny. This interconnected reality becomes even more profound as we look closer to home. The vast supercluster we are a part of, Laniakea, is itself just one component of a far grander assembly, the Pisces-Cetus Supercluster complex. This is not merely a single structure but a complex web of superclusters, a sprawling metropolitan region of the cosmos that may stretch for over 1 billion light-years. Within its immense domain lie famous formations like our own Laniakea, the Pisces-Cetus Supercluster, and many others, all loosely bound together by gravity into one of the largest known structures in our entire cosmic neighborhood. Its discovery was a pivotal moment, revealing that superclusters are not isolated islands in space. They are connected, forming parts of even larger hierarchies, like individual cities linking into a vast, continent-spanning nation. This realization forces us to ask a fundamental question. How does such an immense complex, with its overarching gravitational field, influence the lives of the galaxies within it? The motion and very evolution of a galaxy are subtly shaped by its position in this grand architecture. A galaxy drifting through a dense filament will have a very different history than one isolated in a quieter void. By mapping the Pisces-Cetus complex, astronomers are not just drawing lines on a chart. They are tracing the invisible scaffolding of dark matter that holds this entire structure together. They are reading a history book that details how gravity, over billions of years, has woven these separate clusters into a single, coherent whole. This structure reveals the universe's deeply hierarchical nature, a nesting of scales from local groups to galaxy clusters, to superclusters, and finally to these immense complexes, each level building on the one before in an endless cosmic tapestry. The same cosmic river that defines our supercluster flows toward a profound mystery. Looming in the direction of the constellations, Centaurus and Norma, lies the Great Attractor, a gravitational anomaly of staggering power. This focal point, located roughly 250 million light-years away, exerts a pull so immense that it draws thousands of galaxies, including our entire Milky Way, toward an unseen destination. Its mass is equivalent to tens of thousands of galaxies like our own, a concentration of gravity that challenges our very understanding of how matter is distributed throughout the cosmos. Yet for decades, its true nature remained hidden from our view, obscured by a thick band of gas and dust from our own galaxy's central plane, a region astronomers call the zone of avoidance. It is a profound cosmic irony that our own galactic home blocks our view of the very force that guides its motion. So what could possibly possess such gravitational authority? The sheer scale of its influence suggests this is more than just a massive cluster of galaxies. Its existence forces us to confront the dominant role of dark matter, the invisible scaffolding that shapes the universe's largest structures. The Great Attractor is likely the dense core of the Laniakea Supercluster, a gravitational anchor where the cosmic web's filaments converge. Unraveling this mystery has required ingenious methods to peer through the galactic obstacles, using telescopes that see in wavelengths of light like infrared and radio, which can penetrate the obscuring dust. Each new observation brings us closer to understanding the hidden heart of our local universe, and the ultimate fate of the vast flow of galaxies caught in its irresistible pull. Yet the Great Attractor is not the only massive force guiding our cosmic journey. Looming even farther away, at a distance of around 650 million light-years, lies the Shapley Supercluster, the single most massive concentration of matter in our entire observable cosmic neighborhood. Discovered by the astronomer Harlow Shapley, this colossal structure is not a single entity but a dense metropolis of galaxies, containing dozens of massive galaxy clusters all bound together by gravity. Its sheer scale is almost incomprehensible, a sprawling continent of matter whose collective gravitational pull reaches across the vast intergalactic distances to influence the motion of our own local group of galaxies. We are not just flowing toward the Great Attractor, we are also being subtly tugged by the immense weight of the Shapley Supercluster. This dual influence creates a complex cosmic dance, a gravitational tug-of-war on a scale of hundreds of millions of light-years. How does such a distant supercluster exert such a profound effect on our region of space? Its incredible density and mass warp the very fabric of spacetime around it, creating a gravitational slope so steep that entire superclusters slide in its direction. This supercluster is a key player in what astronomers call large-scale flows, the slow, river-like motion of galaxies driven by the uneven distribution of mass throughout the universe. By meticulously mapping the Shapley Supercluster, scientists are not just cataloging a record holder. They are reading a gravitational map of our local universe, tracing the sources of the forces that have set our galaxy and thousands of others on their long, slow paths through the cosmos. It serves as a powerful reminder that the empty space between galaxies is not truly empty at all, but is instead a dynamic landscape shaped by the invisible hand of gravity, where the most massive structures write the rules of motion for everything else. Perhaps our cosmic address is even more unusual than we realized. While we are part of a vast supercluster, our immediate neighborhood appears to be remarkably empty. This is the proposal of the KBC Void, a model named for astronomers Keenan, Barger, and Cowie, which suggests our local group of galaxies resides inside a cosmic void roughly 2 billion light-years across. This is not a complete emptiness, but a relative underdensity, a region where the number of galaxies is significantly lower than the cosmic average. We are not looking at a void from the outside, we are living inside of it. This idea immediately challenges a foundational assumption in cosmology, the Copernican principle, which suggests there is nothing special about our place in the universe. If we are sitting in a vast cosmic bubble, then our local observations are not of a typical region. They are inherently biased. The most profound implication of this concerns one of the most critical numbers in all of cosmology, the Hubble constant, which measures the current rate of the universe's expansion. If we are living in a local underdensity, the gravity of all the missing matter around us would subtly alter how we see galaxies recede from us. Our local measurements of cosmic expansion could be slightly off, not because our instruments are wrong, but because our vantage point is skewed. This single idea could help resolve a growing tension in astronomy, where different methods of measuring the universe's expansion rate yield conflicting results. What if the discrepancy is not an error in our physics, but a consequence of our cosmic location? The KBC Void model invites a deeply humbling perspective. It suggests that to truly understand the universe, we must first account for the possibility that our own backyard is an outlier, a quiet suburb in a cosmos whose bustling metropolitan centers lie far beyond our current view. This mysterious pull toward the Great Attractor and the Shapley Supercluster may only be part of a much larger and more baffling story. There appears to be a coherent motion on a scale so vast it defies conventional explanation, a phenomenon astronomers call dark flow. Imagine countless galaxy clusters like leaves caught in a river, all drifting in the same direction. This is not the gentle pull of a nearby supercluster, but a relentless current detected across billions of light years. Scientists first observed this eerie movement in 2008 by studying the cosmic microwave background, the faint afterglow of the Big Bang. They noticed that these distant galaxy clusters were moving with a shared velocity, seemingly tugged toward a specific point on the sky that lies far beyond the edge of our observable universe. The very idea is staggering. It suggests that structures of unimaginable mass, residing in a realm of space we can never see, are exerting a gravitational influence on everything we can observe. What could possibly possess such power? The gravitational pull required to move entire clusters on this scale points towards something colossal, perhaps a concentration of mass so immense it lies outside our cosmic horizon. This revelation directly challenges the standard model of cosmology, which assumes the universe is largely uniform and that no such large-scale coherent flows should exist. The controversy surrounding dark flow is intense, with some scientists questioning the data and others seeing it as a necessary paradigm shift. Its existence invites profound speculation. Could we be feeling the gravitational tide from another universe in a vast multiverse, a neighboring cosmic bubble brushing against our own? Or is it evidence of a pre-Big Bang structure, a relic from a time before time whose imprint still guides the motion of the cosmos? Dark flow pushes at the very boundaries of what we can know, suggesting that the story of our universe may be far grander and more deeply interconnected than we ever dared to believe. Even this immense dark flow may be a consequence of a deeper cosmic architecture, one that reveals itself in graceful, almost impossible curves. In 2021, astronomers mapping the distant universe discovered a formation so vast and so symmetrical, it immediately challenged our understanding of cosmic structure. They named it the Giant Arc, a nearly symmetric curve of galaxies spanning an astonishing 3.3 billion light-years. This is not a solid ring but a graceful, crescent-shaped arrangement traced by the brilliant light of distant quasars and galactic clusters. A cosmic filament bent into a profound arc on a scale that defies easy explanation. Its discovery was not the result of a single telescope image, but of patient, large-scale mapping, piecing together the positions of millions of objects to reveal a pattern hidden in plain sight. The sheer geometry of the Giant Arc is what makes it so baffling. According to our established models of the universe's evolution, there simply has not been enough time since the Big Bang for gravity to pull matter into such a coherent, symmetric structure on this colossal scale. The universe's expansion should work against the formation of anything so immense and so organized. So how does something like the Giant Arc exist? Its perfect curvature suggests the influence of unknown physical processes that operated in the early cosmos, forces that may have imprinted these vast patterns onto the fabric of spacetime long before the first galaxies ever formed. Perhaps it is a relic of cosmic inflation, a frozen ripple from the universe's first explosive moments, now revealed by the galaxies that line its curve like lights on a celestial highway. This recent discovery is a powerful reminder that our maps of the cosmos are still incomplete. Just when we think we understand the rules, the universe unveils a structure of such elegant scale that it demands we look again, and think again, about the fundamental forces that write the story of everything. Our own galaxy's brilliant disk has long blocked a colossal secret from our view. Hidden behind the southern obscuration of the Milky Way, a structure of almost unimaginable scale has remained unseen until very recently. This is the South Pole Wall, a curtain of galaxies stretching an astonishing 1.4 billion light-years across the cosmos. Discovered in 2020 through innovative analysis of new galaxy survey data, this immense formation is not a solid barrier but a vast, interconnected filament of the cosmic web. A great wall that rivals even the Sloan Great Wall in its sheer scale. Its detection marks a triumph of modern astronomy, proving that some of the universe's grandest features have been hiding in plain sight, masked by the dust and stars of our own galactic home. To map its true extent, scientists had to look not just with optical telescopes, but with instruments that peer through the obscuring veil using the subtle motions of galaxies to trace the invisible dark matter scaffolding that holds it all together. The existence of the South Pole Wall forces a profound question. If a structure this immense could remain hidden for so long right on our cosmic doorstep, how many other colossal features are still waiting to be found, concealed behind other galaxies or lost in the depths of space? This discovery is more than just another entry in a catalog of large objects. It is a powerful reminder that our map of the universe is still profoundly incomplete. Every time we develop a new way to see, we peel back another layer of the cosmic onion, revealing a geography vaster and more complex than we ever anticipated. The South Pole Wall stands as a testament to the ongoing journey of discovery, a challenge to our ingenuity, and a promise that the cosmos still holds immense secrets just beyond the edge of our current vision. While some structures challenge the rules of cosmology, others help us write them. The Boss Great Wall, a cosmic complex identified in 2016, is not merely a vast formation spanning over 1 billion light-years. It is one of the most precise scientific instruments we have for measuring the universe itself. This immense network of superclusters was mapped by the Baryon Oscillation Spectroscopic Survey, a project dedicated to charting the large-scale structure of the cosmos with unprecedented detail. Its true value lies not just in its staggering size, but in the subtle pattern it reveals, a cosmic fingerprint from the dawn of time known as Baryon acoustic oscillations. Imagine the early universe as a hot, dense soup of particles and light. In that primordial fluid, pressure waves rippled outward, much like sound waves moving through air. When the universe cooled enough for atoms to form, these waves froze in place, imprinting a preferred scale on the distribution of matter. Billions of years later, this fossilized echo manifests as a subtle tendency for galaxies to be separated by a specific distance, a cosmic ruler etched into the fabric of space. The Boss Great Wall provides a perfect, large-scale canvas on which to measure this ruler. By studying the precise spacing of its countless galaxies and clusters, astronomers can measure how this standard length has been stretched over cosmic time by the expansion of the universe. This is where the mystery of dark energy comes into sharp focus. The measurements from Boss and structures like it have confirmed that the universe's expansion is not slowing down, as once expected, but is actually accelerating. What force could possibly overcome gravity and push the cosmos apart at an ever-increasing rate? The Boss Great Wall serves as a crucial testing ground for our models of this mysterious dark energy. Is its strength constant, or does it change over time? The answers are written in the spatial relationships between the galaxies of this Great Wall. This structure beautifully bridges the immense scale of the cosmic web with the most fundamental questions in physics, turning a colossal arrangement of matter into a delicate instrument for probing the ultimate fate of everything. Far to the south, another immense structure weaves itself into the grand Pisces-Cetus complex. The Horologium-Reticulum Supercluster spans roughly 550 million light-years, a sprawling network of galaxies anchored by its namesake clusters. These dense nodes, like bustling cities within a vast country, are where thousands of galaxies gather in close proximity, pulled together by immense gravitational forces. The formation of such a supercluster is a slow cosmic dance dictated by the invisible scaffolding of dark matter. Over billions of years, gravity tugs gently on these primordial strands, drawing galaxies along filaments toward the densest intersections. Within the Horologium-Reticulum, astronomers can witness the dramatic consequences of this process, as entire galaxy clusters undergo violent mergers. These colossal collisions are among the most energetic events in the universe, heating vast clouds of gas to incredible temperatures and triggering bursts of new star formation. By studying the history written in this supercluster, we gain a clearer picture of how galaxies themselves are assembled. The largest elliptical galaxies we see today are likely the products of such ancient mergers, built up over cosmic time through a series of collisions and acquisitions. What does the specific arrangement of galaxies within Horologium-Reticulum tell us about the underlying dark matter that holds it all together? The way matter is distributed here acts as a fossil record, preserving clues about the conditions in the early universe and the nature of the mysterious substance that makes up the majority of its mass. This supercluster is not a static monument but a dynamic, evolving entity, and by observing its current state, we are effectively looking back in time to understand the long-term forces that build the largest structures in existence. Closer to home, a different kind of cosmic architecture reveals the intricate details of the grand design. Stretching through the sculptor region of our celestial sphere is the Sculptor Wall, a vast sheet of galaxies that forms a prominent part of our local cosmic web. While its scale of a few 100 million light-years is modest compared to the distant giants, its significance is immense due to its proximity. This wall includes famous clusters like Sculptor and Fornax, dense cities of galaxies that act as anchors in this sprawling suburban expanse. Its relative nearness transforms it from a distant point of light into a living laboratory. Here, astronomers can observe the subtle dance of galaxies with a clarity impossible for more remote structures. They can watch as galaxies, pulled by the collective gravity of the wall, slowly stream along its filaments, sometimes interacting, sometimes even merging in spectacular collisions. This proximity allows us to answer a fundamental question. How does a galaxy's address within a vast structure like a wall influence its very nature and life story? The environment within the Sculptor Wall is a key factor. A galaxy drifting through a dense cluster at the wall's intersection will experience frequent gravitational encounters with its neighbors, often losing its gas and becoming a quiet, elliptical galaxy where few new stars are born. In contrast, a galaxy residing in a quieter, sparser filament of the wall may retain its gas, allowing it to maintain a graceful spiral shape and continue forming new generations of stars. The Sculptor Wall provides a clear view of this cosmic environmentalism, demonstrating that a galaxy's morphology and future are not just determined by its internal processes, but are profoundly shaped by its place in the vast cosmic community. By studying this nearby wall, we gain a foundational understanding of the universal rules that govern galaxy evolution everywhere, seeing in our own backyard the same processes that sculpt the most distant reaches of the observable universe. Far from the familiar structures of our local universe, the Lynx-Ursa major supercluster drifts in the depths of space, a sprawling complex of galaxy clusters located some 2.5 billion light-years away. Its immense distance is its greatest gift to science, for the light we receive from it today began its journey when the universe was far younger. By studying such a remote supercluster, astronomers are not just looking across space, they are peering back in time, observing the cosmic web at a different stage of its evolution. How does the architecture of Lynx-Ursa Major compare to the superclusters we see closer to home? This comparison is crucial for testing our models of cosmic growth. The patterns we observe suggest that while the fundamental rules of gravity and dark matter remain constant, The universe's structures were more tightly packed and perhaps still actively assembling in that earlier era. Discovered through meticulous redshift surveys, which measure how much the universe's expansion has stretched the light from its galaxies, this supercluster helps trace the large-scale architecture in the northern celestial hemisphere. It serves as a vital data point, a single frame in a cosmic film that shows how diffuse clouds of matter gradually collapsed into the vast, interconnected filaments we see in the modern universe. The Lynx-Ursa major supercluster is more than a distant landmark. It is a chapter in the biography of our cosmos, revealing how its grandest designs mature over billions of years, growing from faint whispers in the primordial dark into the immense heavens that define space today. The northern constellation, Corona Borealis, holds a celestial crown of galaxies, a supercluster whose true value lies not in its size but in its violent perfection. This dense concentration of galaxy clusters forms a remarkably symmetric structure, an almost balanced arrangement that makes it a perfect natural laboratory. Within this cosmic arena, astronomers are witnessing a slow-motion collision of epic proportions, as entire galaxy clusters, each containing thousands of galaxies, are merging together. These are not fast, chaotic crashes, but a deliberate, gravitational dance unfolding over hundreds of millions of years. The space between the galaxies is not empty. It is filled with a superheated gas known as the intracluster medium. When clusters collide, this gas is compressed and heated to staggering temperatures of tens of millions of degrees, causing it to glow brilliantly in X-ray light. Yet something strange happens during these collisions. Observations reveal that a significant portion of the mass seems to be missing from the scene of the crash. The hot gas, detected by our X-ray telescopes, slows down and interacts, but the galaxies themselves and, crucially, the invisible dark matter, appear to pass right through the chaos largely unaffected. This ghostly behavior is one of the strongest pieces of evidence for the existence of dark matter. It suggests that dark matter does not interact with light or with itself in any way we can detect. It only feels the force of gravity. By studying these mergers in the Corona Borealis Supercluster, scientists are not just watching a spectacle. They are conducting a fundamental experiment, testing the very nature of the universe's most elusive substance. The way these clusters tear through each other reveals the rules, or lack thereof, that govern the dark side of the cosmos, offering clues that are as profound as they are perplexing. Our own galactic neighborhood is nested within a structure once considered the pinnacle of cosmic organization, the Virgo Supercluster. This vast expanse, spanning 110 million light-years, contains our local group of galaxies and is dominated by the immense Virgo cluster at its heart. For decades, this was our recognized cosmic address, the largest structure we knew. Its discovery marked a turning point, revealing that galaxies are not scattered randomly but gather into these immense familial groups. Now we understand the Virgo Supercluster is but one lobe of the far grander Laniakea Supercluster, a suburb of an immense heaven. This reclassification beautifully illustrates the hierarchical nature of the cosmos. We live within a local group, which resides within the Virgo Supercluster, which is part of Laniakea, which itself is a thread in the even larger Pisces-Cetus complex. It is a cosmic nesting doll, with each level of scale governed by the same relentless gravitational forces. How does our position within this local supercluster shape our view of the universe? It grounds our exploration, offering a nearby template for understanding the distant giants we have explored. The dense core of the Virgo cluster, with its thousands of galaxies, shows us what a bustling galactic metropolis looks like up close, while our own quieter location on its outskirts provides a clearer view out into the deep cosmos, less obscured by local light and dust. The Virgo Supercluster is our foundational map. the familiar local terrain from which we venture out to comprehend the universe's most colossal and mysterious architectures. These galactic walls are not just distant giants. They are the local streets and neighborhoods of our cosmic city. In the southern sky, the Fornax Wall weaves together the Eridanus and Fornax galaxy clusters into a single, connected structure. Its scale may be modest compared to the billion light-year giants, but its proximity makes it an essential laboratory. Here, astronomers can watch the subtle gravitational currents that guide galaxies along the cosmic web's filaments, observing how these flows slowly but surely deliver galaxies from the sparse voids into the dense, bustling clusters. This migration has profound consequences for a galaxy's life story. A spiral galaxy, rich with gas and actively forming stars, might drift into the crowded core of the Fornax cluster. As it does, the intense gravitational environment can strip away its gas, halting star formation and transforming its structure. This final structure demonstrates a universal cosmic principle that architecture operates on every scale. The same gravitational rules that build the immense Hercules-Corona Borealis Great Wall also govern the local dynamics of the Fornax Wall. It reminds us that whether we are looking at the largest structures imaginable or the familiar clusters in our own backyard, we are seeing different expressions of the same cosmic web, a single, interconnected system that defines the universe from its grandest dimensions down to our own galactic neighborhood. These 20 cosmic structures are not merely a catalog of curiosities. Together, they form a body of evidence that is actively reshaping the foundational principles of cosmology. The sheer scale and number of these immense formations, from great walls to vast voids, present a consistent challenge to the long-held idea of a smooth and uniform universe. The cosmological principle, which suggests the cosmos should look roughly the same in every direction on the largest scales, is being pressured by the discovery of a reality that appears far more textured, heterogeneous, and richly structured than we once believed. This growing understanding has profound implications for our models of cosmic inflation and the mysterious nature of dark matter. The patterns we see suggest that the initial conditions of the universe, set in the first fraction of a second, may have been far more complex, seeding the growth of these colossal features from the very beginning. Our maps of the dark matter web, inferred from the galaxies we can see, must now account for a cosmos where emptiness and density exist on scales that once seemed impossible. The journey does not end here. A new era of discovery is dawning with powerful instruments like the James Webb Space Telescope and the Vera C. Rubin Observatory. These observatories will peer deeper into space and with greater clarity than ever before, mapping the distant cosmos in unprecedented detail. They will look back to the epoch of the first galaxies, tracing the infant threads of the cosmic web as they began to form. What undiscovered giants might these tools reveal? Could there be structures so vast they make our current record holders seem provincial? The ongoing quest to chart the cosmos guarantees that our view of space is not a finished picture, but a living document, continually revised and expanded by technological ingenuity and relentless human curiosity. The universe has proven itself to be a place of grand and surprising architecture, and the next chapter of the map is waiting to be drawn. Our journey across 20 colossal cosmic structures has revealed a universe of breathtaking scale and profound mystery. These are not just distant points of light. They are the grand architecture of reality itself, a filamentary cosmic web woven by the invisible threads of dark matter and the relentless pull of gravity. Each discovery, from the Hercules-Corona Borealis Great Wall to the local Fornax Wall, chips away at our simplest assumptions, challenging the very idea of a uniform cosmos and expanding our comprehension of the forces that shape everything. We have seen that the universe is a place of immense textures, of vast walls and profound voids, a hierarchy of structures that builds from our own galactic neighborhood to formations so large they test the limits of cosmology itself. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That sentiment echoes through every one of these discoveries. They remind us that our quest to understand the cosmos is an ongoing story, a narrative written in galaxies and gravity that is far from complete. Let this exploration be an invitation. The next time you look up at the night sky, see it not as a static ceiling, but as a dynamic map to these incredible structures. Follow the latest breakthroughs from powerful new observatories, for they are constantly redrawing our cosmic charts. We want to know which of these 20 structures redefined your own view of space. Was it the immense pull of the Great Attractor, the baffling emptiness of the Boot's void, or the eerie coherence of dark flow? Share your thoughts in the comments, and if this journey has inspired you, subscribe for more voyages into the universe's deepest mysteries. The cosmos is vast, and our exploration has only just begun.